In this second part of the Grosvenor basis lecture, we're going to talk about a very nice application, the solving polynomial systems. So we consider today the problem of solving a system of polynomial equations, and we concentrate in the zero-dimensional case. That means that the system has only a finite number of solutions, isolated points, not a curve, just the points. So assume that we have a system, G1 equals to 0, G2 equals to 0, and so on. We associate to it the ideal generated by G1, G2, Gn. Then any other set of generators for the ideal I, it gives a system of f1 equals to 0, fm equals to 0, which is equivalent to the system we started from. So we can modify the generators of the ideal. We start this investigation today by reverse engineering some tests to try our code on. So we choose the output we want to get, the set of points, and we generate the input, a system with those solutions. So the problem we start from is, given a finite set of points, x, we want to find the ideal of all the polynomials vanishing in those points. The easy case is just for one point. So say that we want the solution 3, 4, 5, and then the ideal, the polynomial, the ideal giving those solutions is x equals x minus 3, y minus 4, and z minus 5. I get the point 3, 4, 5. And for a set of points instead, I can compute the intersection of the ideals for the single points, and I get an ideal having the solutions this finite set of points. So the intersection of the ideals gives the union of the solutions. This is very hard computation. We haven't seen it, but we can use Grosvenor basis to compute the intersections. But these computations can get quite hard. But here we are investigating points, and there is a very nice algorithm to compute the ideal of points. So here you can read more about this in the manual of CoCoA. This is based on a much more efficient implementation that, instead of using intersection, uses linear algebra to compute the ideal of points. You can find, we wrote a paper about this, and you can find in the literature. So let's create an example to play with. So I set the polynomial ring first, and then I choose some points. I create some random points. So I have 3 coordinates, 1, 2, 3, random number between minus 99 and 99, and then I repeat it 6 times. So I got 6 points with random coordinates. Then I call this magical function in CoCoA, which computes the system, and here is the system. So this ideal annihilates in those 6 points. Now remove all this, and let's pretend we don't know what this system is about, and we want to solve this system. So the first thing we need to ask is this a zero-dimensional ideal? Which means, is this just isolated points? And we do this by checking the dimension of L modulo LT of I. And this is gives 0, so it is zero-dimensional points, single point. Then I ask for the multiplicity, which gives me the number of points. So without doing anything, I have that the solutions of, without doing any, we did quite a bit of computations, because to compute LT, we need to compute the Grosvenor basis of this idea. But without getting really into it, we can already know these two numerical informations, which is 0-dimensional and 6 points. 6 is actually the dimension of P modulo LT of I as a vector space. And this is a vector space basis for P modulo LT of I. So, you know, another function in CoCoA, which might be useful for you. So the first step to compute the actual solution is to compute a univariate polynomial in the ideal I. And this can be done with elimination, again, an application of group basis, or with this function, which is called mean poly. You can get some information in the manual. But just to give you an example, in our case, if I asked the polynomial, the minimal polynomial of x written in the indeterminate x is this polynomial of degree 6. So I'm not explaining here why we need 2, because the function is very general, not just for indeterminates. But so we want to make a nicer syntax, so we make a handy function to call it univariate polynomial with giving the ideal I returns mean poly quot xix. And then I implement this function univariate polys, which computes all of them for all the indeterminates. And so makes the list of univariate polynomial in big X, where big X is any indeterminate. So let's call it. Here it is. Here we have 3 polynomials which capture the projection of the 6 points over the axis. So we notice that we have this polynomial which is of degree 6. So that means that the root of these polynomials are the 6 values for the 6 points. So we compute the factorization. And we get this, which is a record, which corresponds in C++ to a struct or a class. And so we have 3 fields, the factors themselves, the multiplicity of the factors, in this case they're all simple factors, and the remaining factor, which is the leading coefficient of my polynomial divided by the leading coefficient of these, so which is 1 in this case. So nothing that is interesting for us, really. The only interesting thing is the factors themselves. So how do we select the factors? Just writing dot factors, like in C++. And here are the factors. So now that I have the factors, I can add the first factor, x minus x plus 6, which means that x plus 6 is equal to 0, so that x equals to minus 6. So I add this to the original ideal, and computing the reduced Grosvenor basis, I get this Grosvenor basis, which tells me that x is minus 6, y is minus 22, and z is minus 36. So I can do this for all the factors of my polynomial in X, and I get 6 small systems which correspond to each solution. And here the explicit solution I computed by doing X, the normal remainder of X respect to S, and for the same for Y, same for Z, for S, a system in the small system collection. And then here it is. Yeah, I have the 6 points, which are the solutions of our system. So how can we be sure that these are the solutions? Well, we knew this system had 6 solutions. We found 6 solutions, and we just verified that these are solutions. So we evaluate f in each of the points, varying f in all the generators of I, which means the equations of the system, and for being put in points, which is the solutions. So, and indeed, evaluating each polynomial in each point, we always get 0. So these are the 6 solutions of my system. In this case, we know the story of the system, so we can go and check if these solutions are the points we started from. But we must be careful because these are lists of points and not set of points. A list of points, so they might be sorted in a different way, the 6 points. So we need to call the function EQSet if we want to compare 2 CoCoA lists as sets. So disregarding the ordering on the sorting of the 2 lists. Okay, very good. So we found the solutions for this system, but we can have problems if I just don't know what the system is. What if I don't know the solution of the system? It might be hard to find the solution of the systems. And now we see what kind of problems we can get. One problem is the problem of multiple points. If we might have that our system has multiple points instead of simple points. How do we detect this? So let's see a very trivial example. So I put the setting of the plane. So, and I consider this parabola intersected with a vertical line and with a horizontal line passing through the origin. So they both, the origin, the point 3, 0. So they both intersect in the same point, but in this case, the intersection has multiplicity 1, and in this case, the intersection has multiplicity 2. Do we see that in the ideals? Of course we do. So these are the leading term, and we see that the leading term of the 2 ideals are actually different, because here we have an x squared, and here we have just x and y. The dimension is 0 for both of them, so we do get that in both cases there are isolated points, but in this case, we see that the number of points is 2 because the point is computed with multiplicity. So how do we get rid of this problem? We need to get rid of the square. And so let's see first for a single polynomial. If we have a single polynomial, we have a function in CoCoA computing the radical of the polynomial, which means that it returns a polynomial with the same factors, but which is square free. And so from this polynomial, we get rid of the 6 bar in the second factor. Okay, so if we apply these functions to all the univariate polynomials, we get, in this case, we get x minus 3 and y. In the special case of 0-dimensional ideal, computing the radical is easy, so to speak. We just need to add to the original ideal all the radicals of the univariate polynomials. So we have already computed the univariate polynomials. We computed the radicals. So this is the list of the radicals of the univariate polynomials. We add these 2 polynomials to my original polynomial, and I get, as a result, the radical of the original ideal. Remember, this works for 0-dimensional ideals only. So after doing this, the multiplicity is 1. So it is, I removed the multiplicity of the solution of the point. Just to get a little insight, this is highly optimized in CoCoA. So if I compute the radical of an ideal, it does some computation in a slightly more clever way, but it is based on this construction I have just told you. So especially I want to show you that I do some computation with the Grobner basis giving a time limit, which can be handy in some of your projects. If you want to know more about this, there is a paper about mean poly we wrote in 2020. We published in 2020. It was older than that. So set the verbosity back to 0. So in conclusion, always check if the input ideal is radical. If not, you compute the univariate polynomials and add the radicals to it, or you call radical from CoCoA. Okay, we may have other problems, and the other problems are align points. So think of putting points in a grid. So if they're in a grid, they share the same x or the same y. So let's construct an example where several points share the same coordinates. Here it is. So I put 3 coordinates back in, and these are 9 points, and we see these 9 points. For example, we have 2 points with x equal to 3. We have these 2 points with y equals to 0, and we have these 2 points with z equals to 3. So what happens? We compute the ideal of points. This is the ideal. Again, we forget how we computed the ideal, and we start again. First question, is this a zero-dimensional ideal? Yes, it is. Very good. There are points. What's the multiplicity? What's the number of the points? The solutions? 9. Very good. Are there simple solutions, simple points? Yes, it is radical. Very good. Okay, now we compute the univariate polynomials. We look at them. When we look at them, we see that there is no polynomial of degree 9, which means that I don't have any polynomials which gives me the 9 coordinates for the 9 points. So it means that there are repeated coordinates in these points. How can we solve this problem? We take our grid of points, which is represented by a system, and we move it slightly. If we move it slightly, then we get, we break the alignment. So we take a random polynomial, which this is not very random. We substitute, instead of z, I put this random linear polynomial, and I compute the polynomial in z. And if I look at the polynomial in z, I see that that's not good. It's not enough. I get 6 different coordinates. I need 9. So the degree is too low. I take a more random polynomial. This is pretty random. I substitute z with this new polynomial. I compute the univariate polynomial. Okay, it is of degree 9. So with this polynomial, I get the 9 coordinates. But the coefficients are big. Coefficients are big, and when coefficients get big, computations get hard. So I take another linear polynomial, which is random but smaller. I compute it, substitute to z this linear polynomial. I compute the univariate polynomial, and I get a polynomial degree 9, which is good, and where the coefficients are smaller. Small enough for CoCoA, not for me to do computations by hand, of course. So this is good. This is better, and then I use this polynomial here. What did I do before when I had a polynomial with the right degree? I compute the factors, and the factors gives me the value, the 9 different value for z. Then I use these values to compute the 9 small system, as we did before. And then I use these small systems to get the points, and these are the points. And at this point, you should be thinking, wait a second, you're cheating, because I started from a system, I changed the system, and I gave you the solutions. Of course, these are the solutions of the moved system, not the original system. So now I have to make the transformation back to get the points of the original system. So I have to undo the change of coordinates, and this is the way I do. So I don't know if that happens to you, but when I have to undo a change of coordinates, I always get confused, and I don't know if I'm doing it right or I should do it the other way, but I checked. This is the right way. And here are the points. Are the points we start from? Are these the solutions of the original system? Of course, we can verify these new points. We evaluate the 9 points in all the generators of the ideal, and we always get 0. So these are the solutions, all the solutions of my polynomial system. Nice. So I suggest you this exercise for you to get used to these constructions. Invent an example with 12 points with some aligned coordinates, and then you create the system with ideal points, and then you solve the system and verify the answer following the steps we did. At the end, we talk about non-rational points, because of course, if I write the points are rationals, because in CoCoA I can only write rational numbers, integer or rational numbers. But what happens if I take an ideal like this one? I write an ideal, I have no idea what the solutions of these systems are, but I can compute the dimension, 0-dimensional. Okay, so there is only points as solutions, and there are 20 points as solutions. We learned that the first thing we have to do is ask, is this radical? And it isn't. Okay, it is not radical. Indeed, we see it from the input. It is not radical, there is a square. So I take the univariate polynomials in the x, y, and z. We compute the radical of these, and I don't even print them out. I add them to the ideal. I know that it is in a 0-dimensional ideal. If I add the radical of the univariate polynomial, I get the radical of the original ideal. Okay, so radical I is the radical of the ideal, and the multiplicity gives me 10. So there are 10 points of multiplicity 1. Okay, then I compute the univariate polynomials. Okay, this time I'm lucky because there are no aligned points. Each of the univariate polynomials has degree 10, so I can find the roots, the 10 coordinates of the points. And then I computed the factorization, and nasty surprise. Nasty surprise. Here, what I have is that the factors is just one factor, and is the polynomial itself. And that means that these 3 polynomials, all 3, are irreducible over the rationals, because CoCoA makes exact computations. So the factorization is over the rationals. What can we do at this point? We cannot find with the factorization the coordinates, the x coordinates. So we now use something very powerful. We use the lexicographic Gromner basis, and we saw one of the previous lectures that the lexicographic group basis seems to have a nice shape. And indeed, there is a theorem which is called the Shape Lemma, which tells us that in the nice conditions where the ideal is radical, there are no alignments in the points, then the lexicographic group basis has a very nice shape. And this is it. We have one polynomial in the smallest indeterminate, which is z, univariate. And then we have that x is an expression in z and y is an expression in z. This is the shape lemma. The shape lemma tells us that in these conditions, we always have a group basis like this, with the univariate polynomial. From the univariate polynomial, I can compute the solutions of a univariate polynomial, and then I substitute these solutions in the other two expressions to get the values for x and y. So I give meaningful names. So the first polynomial is in the z polynomial, and the second polynomial is for y, and the third polynomial is for x. So it's easier to remember. Now, how do we find the real root of a polynomial? This is a chapter by itself, and John Abbott is an expert about this. And he implemented an algorithm in CoCoA to compute the real roots of a polynomial. So what is the common strategy is that when you know a polynomial has roots without multiplicity, then you can make a isolating interval for each of the root of this polynomial. And then when you know that the root is in an interval, you can refine this interval and make it smaller and smaller. Like a bisection method, and you can find a very good approximation for your real solution. So this method is called quadratic interval refinement, and you can find more information in a paper by John Abbott in 2006 and 2014. So let's see it in action. We take the real roots with 50 digits of precision. And here are the roots. This is a bit disconcerting because you're talking about real roots and you see a whopping rational number. So we use this function floatstr, which makes a string representing the floating point representation. And here we see that out of those 10 complex roots that we were expecting, only 2 are real. So we had a polynomial of degree 10, and only 2 of the solutions of the roots of these polynomials are real. Okay, that's all we can get. We cannot compute the complex solutions in CoCoA, but we conclude many real-life problems. You are interested in the real solutions, not all the complex solutions. So that's already pretty good. So the points, so these are the 2 values for z of the 2 real points. And then we substitute in the 2 polynomials for x and y. In this way, we evaluate the polynomial in 0, 0, z, and the x polynomial in 0, 0, z, and the y polynomial in 0, 0, z, and I get the coordinates for the points, all 3 coordinates of the point. And here I ask CoCoA to write with 15 digits. So this are the coordinates for the first point, and these are the coordinates for the second point, the real solutions of the polynomial system. Can we verify the answer? Well, we cannot verify it exactly because these are not rational points. We already know these are not rational points. Otherwise, we would have known by the factorization. So we know that these are not the exact solution because these are rational numbers. But we can evaluate we bring in the original generators in my new polynomial ring, and we do the same as we did before. We evaluate all the polynomials in all the points and see what happens. And what happens is that we get something which is not exactly 0, but pretty close to 0. Of course, when starting an application, you need to know what is the range of the precision that you need, and then you need to take care of this precision is good enough for you. But this means that is 10 to the minus 27 is 77 is pretty close to 0. So some interesting exercises you can do after this presentation is try to solve this system and see what happens. Or another even more interesting exercise, invent your own system and solve it and see how many solutions you get. And here is a very intriguing example. So you can see what happens when you have a system depending on the parameter and you wobble the parameter a bit, and you see how the number of solutions varies when you change the parameters. So this is all we see in these lectures about group bases in CoCoA-5. And soon we will see something in CoCoA-lib, which is the mathematical core of CoCoA-5. Bye. See you later.